Hello everybody, and welcome to Lab 3 Part 2. In this lab we are going to do least squares estimation of the motor model obtained from the GP6 data. The thing is that for this lab you do not really need to take the data again because you already have the data from the previous lab. So for many of you, when you do this lab, actually you can just use the previous lab's data, or if your data is corrupt you will need to take it again. Now what we will show you is how to do this lab, and we are not going to take data again from the GP6 because we already have it, so we'll just execute our code on it and show you what we get. But here's what this lab does, and we are trying to do something called as least squares estimation. So we are trying to generate or estimate the step response of our model and compare it with the simulated one. But the model in this one is the GP6 itself, because we are going to use the impulse response data from the previous lab that we had using the GP6. So this is the transfer function you had in the continuous time. You made a discrete version of it and then you got its impulse response, and then we built the same one using the GP6 and made a PRBS signal, put it through the GP6, took the output of the GP6 and calculated the impulse by correlation analysis. This is what happened in the previous lab. In this lab we are going to take the same data, the impulse response data that you got from the previous lab, and run a least squares estimation code on it. So here's how it goes. If, let's say, these are the matrices that you have to build for this lab. So in order to understand that, you need to see that your discrete transfer function is going to look something like this. As g of z equals a of z inverse plus b divided by z inverse plus c. That is the first order transfer function in the z domain. If you solve this out and you go through all the steps and bring it back in the form of a difference equation, this is what you will get. Y hat of n equals a over c u of n minus 1 plus b over c u of n minus 1 over c y of n minus 1. Now y in this equation is the output, which for our case is the output data or the impulse response data that we obtained from the GP6 in the last lab. U of n is our PRBS signal that we generated. Once you are done finding this equation out, what you can see is we make this phi or phi matrix. This matrix has nothing but these elements from this equation down here repeated in it. So the first column is u of n minus 1, the next one is un, and the last one is, please note the negative sign, it's minus y of n minus 1 to big N minus 1. Now each of the columns contain n elements, where big N is the length of your PRBS signal, and as we remember from the last lab, it's always a power of 2. It's either 512, 256, whatever. Note that the first column is just a shifted version of the second column. So you start at a different index and end at a different one, so the column is off by 1, but otherwise the elements are the same. The last column is also a shifted one, it's shifted by 1, but it's not u, it is your output from the GP6. Okay, this phi matrix is called the regressor input, and once you are done with that, it is very important to check in your workspace in MATLAB that you got the matrix correctly, and indeed your columns are skewed by 1. The elements that you do not have, like say when n is 1, u of n minus 1 would be u of 0, but in MATLAB you do not have vectors starting with an index 0. That only happens in C. Neither do you have vectors with negative indices. Whenever that happens, whenever you have an index for which you do not have an entry, you have to fill in zeros in this matrix.
Yeah, we cannot predict the past.
Yeah, and because you cannot predict what happened before that. So what is next? The next important thing is the theta vector. if you see, the theta vector contains coefficients from this transfer function, a by c, b by c, and 1 over c. It's just repeated there. Just to note that here in the equation it's minus 1 over c, but here we just write 1 over c because the negative sign has already been taken care of in the phi matrix. Now the theta elements, we will call them as theta 1, theta 2, and theta 3. Now comes the least squares estimation part. Now by least squares, the formula of least squares y hat, which is your estimated new y, should be phi times theta, and that should be as close as possible to the y that you originally got. But the formula that we use for this lab is this one, which is the standard least squares formula. It's theta equals phi transpose phi inverse phi transpose y. What we're trying to do is trying to solve for theta. So the phi matrix that you just made, put it in here. The y is just your output vector, put it there. Although this looks like a lot of math and maybe you may not understand it right away, but this is a proved mathematical result and this works. So do not have any doubts on this and do whatever this wants you to do, like multiply the transpose of phi with the phi, then take the inverse of that, then multiply it by the phi transpose again, and then multiply it by the y vector. Once you have calculated this theta as we have here should have only 3 elements, theta 1, 2, and 3. What you do next is you start calculating a, b, and c. You will have theta 1, theta 2, and theta 3. There will be some values in this matrix, in this vector that you get, or the row vector that you get. And so the inverse of the last element will be c. That times, then you can multiply that by the appropriate numbers to find out a, b, and c. Once you have a, b, and c, you have to put it back into this transfer function. Once you have that, and you give the transfer function some sampling time. Remember in the last lab we were changing sampling times. We have to fix on one, like say 0.01 or 0.001. Find out the best one that works for you. So put in a, b, and c, give it the sampling time, and then get a transfer function. Once you have this transfer function, you plot the step response of your original model, which is this one in the S domain, and then your new transfer function in the Z domain. Once you have these two step responses, you can compare how closely they match. They should be pretty close because this least squares estimation method works really well. That's the technical part, but after that what you will need to do is you will need to write similar equations in the difference equation form for second and third order, and then expand them out, make new phi matrices, and get new theta vectors, calculate all the parameters, see what you get as the parameters, put them into the new transfer function, which will be now a fifth order Z domain transfer function or a third order, whichever order you choose, and then you plot the step responses of those against your ideal one. It's helpful to calculate the error. The error is given by a formula